Okay, so we're doing chapter 3, factoring. A little summary here for you all today. We're going to go all the way back to 3.1 and cover everything 3.1 to 3.8. You guys ready? Now, you might want to jot some of this down. If you've got a cue sheet or a study sheet or something that you're making, this is really good. Boys, maybe just while I'm talking, just kind of hold on. If you have a question, feel free. Okay? All right, so all the way back to 3.1, what we did was we determined prime factors. Okay, determine prime factors. That was the first thing. So if you remember, we did this little factor ladder, right? So let's do 64. So 64, you divided that by the lowest prime number that you could think of. In this case, it's always good to start with 2 if it's even, because that's easy. That goes to 32. Okay, and then if you can still divide it by another prime number, then you go ahead and do that again. So I'm going to divide by 2 again. I get 16. Look at all this. 2. I can do 2 again to get 8. And I can do 2 again to get 4, and finally 2 again to get 2. When you get a prime factor on the bottom of the ladder, that's when you stop. And this is a list of all of the prime factors. In this case, in this example, they're all 2's. That's why you see here that the product of prime factors is 2 times itself 6 times, or 2 to the power of 6. For 80, okay, so we do the same thing with 80. Let's divide by 2, you get 40. Divide by 2, you get 20. Divide by 2, you get 10. Divide by 2, you get 5. Now 5 is a prime number, so we stop. And so that's where we get 2 times itself 4 times, and then times 5. So the product of prime factors is prime factorization. Write it as a product. And you can write it out like this, 2 times 2 times 2 times 2 times 5. Or you can simplify this by writing this as 2 to the power of 4. So from there, we can find out all sorts of things. The next thing that we found out in this chapter was greatest common factor, or GCF. So in that way, what you do is you look at the factors on both numbers. Let's see. So the GCF of 64 and 80. What you do is you identify all the factors that are the same. So there's 1 2, there's 2 2's, there's 3 2's, there's 4 2's that are the same. Okay? So that means that 2 to the power of 4 is common, so greatest common factor. So 2 to the 4 is common, so that's the greatest common factor, 16. Okay? So whatever is common to both, whatever numbers are on both lists, you stroke them off and pair them off, and then that's your greatest common factor. The other one that's a little confusing is the least common multiple. So the least common multiple, remember, factors are numbers that are smaller than the original number. Multiples are always numbers that are bigger. So times 1, times 2, times 3, times 4, times 5. So the least common multiple, this is done a little bit differently. So what we do here, and this is a bit of a mess here now, so I'm going to try and erase some of this. But what we do differently for this least common multiple is we take a look at all of the factors. And for example, both lists have factors of 2. And so I look at the list with the largest number of 2's multiplied together, and that's this list over here. 1, 2, 3, 4, 5, 6. So 2 to the power of 6 is recorded. Then I look at the other prime factors, and the only other prime factor that's in either list is 5. And so the largest number of 5's in this row here, this list, would be 1. So that's 5 to the 1. So the least common multiple between these two numbers is 2 to the power of 6 times 5 to the power of 1. So it's the greatest number of prime factors in any list. So you got to count for each prime factor, and you take the largest number of them in each list and multiply those together to get the common multiple. Now there is a way to do this without doing prime factorization as well, and we did that. But it's very good for you to know. This is the more complicated part. So using the prime factor list is important, because if these numbers are big, writing out the factors of 64, let's say, remember we did this, 1 times 64, 2 times 32. What else is there for 64? 4 times 16. All right, so we got 4 times 16. Do we have anything else? 8 times 8. Okay, so here's the list of factors. And if you list that, and then you list the factors for 80 as well, then you would spot 16 as the greatest common factor in both lists. And then you'd have to start over, though, and do multiples. So, 64, 128, 256, 512, 1024, you have to keep going on like that until you had multiples. Oh, wait a minute. is this 64 and 60? Now, is this a typo? 64 and 60, 64 and 80. That should be 80. I think that's just a typo, right? Because I think they're dealing with the same. Yeah, it must be just a typo. Okay, no problem. We figured that out. Yeah, I assumed that was 80. Okay, so that's 3.1. Any questions about 3.1? No, nothing? You got that figured out? Okay, so 3 important things. Prime factorizations, greatest common factor, least common multiple. You need to know how to find those. All right, 3.2. Determine whether a number is a perfect square or a perfect cube or neither. And what we do there, we can, again, use the prime factor list. Okay, use the prime factors. If you have 2 identical groups of factors, then it's a perfect square. Let's take a look at this 64 again. Okay, now watch this. These are all the prime factors. I can split this list exactly in half, and each half is identical. You see? That's 2 to the power of 3 times 2 to the power of 3. So if you have 2 identical factors, and of course that's 8 times 8, right? Then 64 is a perfect square. So if you have 2 identical factors, which are represented by, you know, if the prime factors, you have 2 identical halves. You can split them in half, and they're 2 of them are the same. Then that's a perfect square. A perfect cube, like 8, okay? So divided by 2, divided by 2. Look at this. If you can split all of the factors into 3 identical groups, in this case, a single 2 is in each group. All of the factors are accounted for, and each group is identical. That means 8 is a perfect cube. Okay? Let's see. So look at this. Another way to look at this, 4,225. Is this a perfect square? Well, I have this factor of 5 twice, and this factor of 13 twice. So that means it's a perfect square. Each factor is squared. Another way to write that is this. Watch this. 5 times 13 times 5 times 13. And that will also show you that each half of the factors are identical. So it's a perfect square. And this is the way I like to teach it. If all the factors are squared, you're good. If all the factors are cubed, you're good. Right? Like for 8, okay, we have 1 prime factor, and that's cubed, so perfect cube. That's just another way to look at it. I like to split them up into 3 identical groups, but all of the prime factors, if they're squared, it's a perfect square. If all of them are cubed, it's a perfect cube. Okay. All right, any questions about 3.2? All right, so that's what you're focusing on. Perfect square numbers, perfect cubes. Okay, 3.3. Determine a common factor for a polynomial now. Okay, so if you look at the terms in a polynomial, if you can find a common factor that's in every term, then you can pull that out or factor that number out. In this case, 3 is a factor of all of these numbers. Therefore, 3 is a common factor. But also, each term has at least one y in it. So that means that y is also a common factor. So the real common factor when it's all put together is 3y for this one, okay? Because that's common factor to all the terms. When you've pulled 3y out, then what you do to write the rest of the factored version is you divide 3y out of each term, and you write what's left over. In this case, x squared is left over when I divide 3 and y out. See, just x squared there. If I divide this one by 3, I get negative, because it's a negative divided by positive, 7, and the y's are gone, x is left. So I get minus 7x. And then this one divided by 3 is 10, divided by y is y. And so that's this one factored. Okay? That's the greatest common factor for a polynomial. And that's what we focused on in 3.3. Now, 3, 4, 5, and 6 are multiplying polynomials. Okay, so let's take a look at both of these at the same time. And I feel like I should, sorry, I gotta zoom out a little bit so everybody can see everything. All right, so 3, 4, 5, and 6 are multiplying binomials, so expanding binomials and other polynomials. Okay, that's going to show up. Oh, here's multiplying polynomials in 3.7. So multiplying binomials, and then here in 3, 4, 5, and 6 is also factoring. So multiplying out for binomials, use the FOIL method, right? That's the first terms multiplied together, then the outside terms multiplied together, then the inside terms multiplied together, and then the last terms multiplied together. Another way to look at that is distribution. So we always take each term in our first polynomial and multiply it by all the terms in the second. Then we go to the next one. Multiply this by all the terms in the second as well, and we list them, gather like terms, and simplify. So FOIL method, distribution, which is studied further in 3.7, we have like a binomial times a trinomial. No problem, right? That's still just distribution, expansion. So this one, if I drew the arrows, you take the first term and you multiply them by every term in the other polynomial. Right? There's the product, there's the product, there's the product. Then you go ahead to the second term, which would in this case include the sign there, -4. Multiply that one by each term in the second polynomial, and that's these three numbers. Gather like terms, write your final product there. Okay, so that's multiplying, expanding polynomials. Factoring is where we spent most of our time in the last number of sections. That's a trickier one, I think. Expanding, or factoring. So what you do is you look for GCF always. If there's no GCF, then what you're going to do is you're going to try to find two binomials that multiply to the trinomial. So a trinomial, if it's factorable, will be able to factor down to two binomials. A trinomial gets to two binomials. Now the decomposition method, okay, the decomposition method, which is what this is, 5 times -2 is -10. Factors of -10 that add to -9 would be -10 and +1. Right, sorry, where am I? +1. And so that's how the middle term is decomposed. Remember, that's the decomposition method. Factor by grouping. So group the first two, and then you factor it. Group the second two terms, factor that. And if you have the exact same greatest common factor binomial in each of these sides, then that's what you pull out as your GCF, and then you whatever's left over, in this case 5x plus 1, that's your second term. So that's just a brief description of decomposition method, which you can look back to the lesson if you need to update on that. You could also just do intuition. So again, if you did something like this, what you could do is just run options, right? So just in your head, 5x squared is going to come from 5x and x, you know that. -2 is going to come from either -2 and +1 or -1 and +2. So there's only a few limited options. You can figure that out, and it has to add to -9 when you do the FOIL. So if you put a 2 here and a 1 there, I get 10 and 1. That will combine to give me 9. If I have -10x and +1x. So you could get to this just by intuition or other methods. If I ask you to show me decomposition, you will have to kind of show this process because it is a skill you're supposed to learn in this class. But for the most part, you just have to factor trinomials any way you want. Okay, is that okay? Can we move on from that? The easy ones are with when a is just 1 here. That's easy. I don't think I need to go over that, but let's say you had x squared plus 7x plus 10. Then you would simply two binomials, and you would simply say, what are the two numbers that multiply to 10 and add to 7? And this is x here because that's an x squared, and this is plus 5 and plus 2. They multiply to 10, add to 7, done. That's easy. Special polynomials, the last section 3.8, special polynomials. They are, let's see, perfect square trinomials and difference of square trinomials. Also, I don't think it's mentioned here, but multivariable trinomials. So that's the other one we did, multivariable trinomials. And quickly I'll show you, oh, that's this one right here. This one right here. Okay? All right, and inside this, oh, I guess, yeah, this is a little bit of the perfect square trinomial and the multivariable stuff. So, perfect square trinomials, if this term is a perfect square, including the variables, So if the exponent on the variables is even, then it's a perfect square, okay? And you know what the perfect squares numbers are. You should anyways. Make sure you have memorized or written down on your cue sheet the perfect squares from 1 to 20 probably. So 1 squared, 2 squared, 2 squared, 3 squared, 4 squared, 5 squared, all the way to 18 squared, 19 squared, 20 squared. You need to know those. All right, so this is 5 squared, right? So the square root of this is 5x. So that goes as the first terms. The square root of 49y squared is 7y. And then because it's a difference of squares, you factor this by putting a plus and a minus in between, done. Okay? So square root goes to the first terms, square root of the last one goes to the second terms, and then plus, minus, done. For this one here, I would suggest that you make sure you remember to pull out a GCF, okay, very important. And that's what they did here. They took out a 4 and placed that as a factor right here. After they took out the 4, they ended up with, and I'll show you the middle step here, they had this. Right? And so with the two multivariables right here, this is a perfect square trinomial. So watch this. You know, two brackets. X squared would be x times x. 4y squared would be 2y and 2y. And it just so happens that how you check this term, if it's a perfect square trinomial, is you think about 2ab. That is a times b times 2. Or in this case, 2 times x times 2y. That gives me 4xy, and that's exactly what I have here. So it's a perfect square trinomial. This is a plus, and this is a plus, so these two are pluses. And that's how they got this answer. Okay, now I'm doing this real quick because it's a review. I wouldn't teach it this fast, but this should be a review. So hopefully that makes a little bit of sense. If you need to kind of rewind or back up the video or watch another video, please feel free to do that. But that was generally everything that we covered in Chapter 3. And if you have a good handle on all this stuff, you'll be great for the test. Okay? So 8 sections, it's a lot of sections, all the way back from prime factorization to factoring special polynomials. So it's a big chapter. You have your work cut out for you for studying for this test. Any questions? All right, there's your blitz on Chapter 3.